We're going to take a look at the graph of y equals the absolute value of x. So here's what the graph looks like. It's a V-shaped graph, as we learned earlier. The V-shaped graph has its vertex at 0, 0, or at the origin. So the parent function has its vertex at the origin. The parent function also has an axis of symmetry that goes right through the origin, right through the vertex, and it makes the right side and the left side of the V-shaped graph mirror images of each other. The next thing we need to remember about the parent function is the domain and the range. The domain is a description of all the possible x values that make sense for this graph. So we can see that the point 0, 0 is on this graph. The point 1, 1 is on this graph. So is 2, 2, 3, 3, negative 1, and 1. So the x values of those points, 0, 1, 2, 3, and 0, and negative 1, negative 2, and negative 3, those are all a part of the domain. But is there any number on the x-axis that would not be a part of the domain? Well, the right side of our V seems to continue forever up and to the right. So since it continues forever to the right, the domain will have no restriction. There will be no end to the x's moving to the right. And if we had more and more points on the left side of our graph, it continues to the left and up, which seems like forever. So there will be no limit to the x values that would be valid for this graph. So the domain of this graph is all real numbers. Now, when we look at the range, we're looking at the y values. And here's 3, and here's 2, and here's 1, and here's 0, and here's 3, and 2, and 1, and 0. But it doesn't seem like we'll ever have a y value that goes below the x-axis, because there are no points on our red graph that are below the x-axis. So the domain is all real numbers. The range is the numbers that are greater than or equal to 0, because all of the numbers, all of the points that are on this graph are going to have y coordinates greater than or equal to 0. The next thing that we want to talk about is which part of the graph is increasing and which part of the graph is decreasing. So if we start on the right side of the graph, the x's are increasing. And while the x's are increasing, the y's go from 0 to 1 to 2 to 3. They're also increasing. So while the x values are increasing, the y values are increasing. So the right-hand side of the graph is increasing where x is greater than 0. On this side of the graph, because we're dealing with negative numbers, now as our x's increase, going from negative 1 to negative 2 is an increase. Negative 2 to negative 1 is an increase. From negative 1 to 0 is an increase. So as the x's increase, what happens to the y values? They go from 3 to 2 to 1 to 0. So on the left side of the graph, as the x values increase in value, the y values decrease in value. So the left side of the graph, we would say, is decreasing. Now we're going to compare our graph to the graph of y equals 2 times the absolute value of x. And so this blue graph is y equals 2 times the absolute value of x. And the red graph is our parent function, y equals the absolute value of x. You can see that they have the same vertex. They have the same axis of symmetry that divides them into mirror images. The difference is it seems that the blue graph is narrower. And what that's actually called mathematically is it's experiencing a vertical stretch. So on the red graph, we would go over 1 and up 1. To get to that same point on the blue graph, we would go over 1, but up 1, 2, twice as much. So the graph y equals 2 times the absolute value of x has a vertical stretch of 2, and that's true of any points. If I go over 3 and up 3, I'll be at the red graph or on the parent function. If I go over 3 to get to the blue graph, I need to go up 3, 4, 5, 6. Again, showing that it's a vertical stretch of 2. The previous graphs, the absolute value functions, those are from chapter 1 of our book this year. Now we're going to move into chapter 3, graphing quadratic functions. So the graph that you're looking at now is the graph of y equals x squared. That is the parent function of all quadratic functions. And you can see that it has its vertex at 0, 0. You can see that it has an axis of symmetry at x equals 0, which makes the left side a mirror image of the right side. And you can see that it goes through the point 1, 1, 2, 4, and 3, 9. And on the other side, it goes through the point negative 1 and 1, negative 2 and 4, negative 3 and 9. And so right now, what we can say about the domain and the range of this problem. Well, if we look at the domain, the x values, we definitely have 0 included, negative 1 and 1 are included, negative 2 and 2 are included, negative 3 and 3 are included. But if we look at how wide is this thing going to get on the x-axis, well, it just keeps going wider and wider and wider. So for any x value that we find on the x-axis, that is going to be a valid point somewhere on our red graph. And this graph is called a parabola, the graph of a quadratic function. So the domain is all real numbers. The range is a description of the y values. We have 9 is a point on the graph, 4, that y value is a point on the graph, 1 is, 0 is. But if we look at the pattern now, the y values start going back up again. Positive 1, positive 4, positive 9. So it doesn't look like there's going to be any values from the negative part of the y-axis that are going to be points on our parabola. And so we would say that the range, or the y values, it's the y values that are greater than or equal to 0. We also need to be able to look at the parabola and see when it's increasing or decreasing. So first, let's look at the right side of the parabola where the x values are increasing. What are the y values doing? So as the x's go from 0 to 1 to 2 to 3, the y values are going from 0 to 1 to 4 to 9. So while the x values are increasing, the y values are also increasing. So we would say that when x is greater than 0, this function is increasing because the y values are increasing. Now if we look at the left side of the graph, again, we're talking about negative numbers. So increasing from negative 3 to negative 2 is increasing. From negative 2 to negative 1 is increasing. From negative 1 to 0 is increasing. So as the x values are increasing, the y values are going from 9 to 4 to 1 to 0. So while the x values are increasing, the y values are decreasing. So we would say when x is less than 0, this graph or this function is decreasing, because when you are left of 0, or when x is less than 0, the y values are getting smaller as the x values are getting bigger. Now our graph undergoes a vertical shrink. So if we go over 2, we need to go up 1, 2, 3, 4 to get to our parent function. But our green function is not like our parent function. It is our parent function undergoing a vertical shrink of 1/2. Because when I go over 2, I don't have to go up to 4 to get to my function. I only have to go up half as much, or I have to go up 2. If you look right here, over 1 and up 1 to the parent function. If I look at the green graph, it's over 1 and up 1/2. So by putting 1/2 as our a value, it causes a vertical shrink of 1/2. Now we're going to take a look at y equals negative x squared. So the parent function is y equals x squared. What we're going to look at now is y equals negative x squared. So changing the a from a positive 1 to a negative 1 on the graph causes a reflection over the x-axis. So while our parent function opens up, our new function in purple opens down. So both functions have the same vertex. Both functions have the same axis of symmetry of x equals 0. The main difference between the parent function and the purple function is the domain and the range and whether they're increasing or decreasing. So remember, when we're trying to describe the domain of the purple function, we want to know all of the possible x values of all of the points that could be on the graph. So we can see our domain right now is going to be made up of 0, -1, 1, -2, 2, -3, and 3. But what about the points further down on the graph that we can't see? You should be able to tell that the graph is getting wider and wider and wider and wider and wider, and it's going to continue to get wider forever. So there's no point on the x-axis to the right that is not going to at some point be an x-coordinate of a point on the graph. And there's no number on the x-axis to the left that at some point won't be the x-coordinate of one of the points on the graph. So the domain is all real numbers. Now the range is a description of the y values. So if we look at the pattern made by the part of the range that we can see, -9, -4, -1, 0, -1, -4, -9. So obviously at 0, it turns back around and starts going down again. So it doesn't look like our purple graph will have any points that have positive x values. So when we describe the range of the purple graph, we would say y is less than or equal to 0, because all of the y coordinates will be less than or equal to 0. All right, when is the graph increasing and when is the graph decreasing? So first, let's look at the left side of the graph this time. When are the x values increasing? Well, from -3 to -2 to 1 to 0, those are increasing. What's happening to the y values at that time? They're going -9, -4, -1, 0. They are also increasing. So as the x's increase, the y's are increasing. So we would say if x is less than 0, all of these x's are less than 0. If x is less than 0, then our graph is increasing, because when the x's are getting bigger, the y's are also getting bigger. Now, if we look at this side of the graph, when x is greater than 0, our x values are going 1, 2, 3. As our x values get bigger, what happens to our y values? -1, -4, -9. So as our x's increase, our y's decrease. So we would say when x is greater than 0, this function is decreasing. All right, so hopefully during this video, you've made the connection between the absolute value graphs and the graphs of these quadratic function, or these parabolas that we graphed on the screen. And you see that you already know most of this information. There's some different vocabulary words, and it's a curve instead of a sharp pointed V. But a lot of what we learned in chapter 1 about absolute value graphs will apply to what you're learning about graphing quadratic functions.